Morning and hot.
Good morning, guys, and welcome to week 4 of astronomy. This is week 3, I'm sorry, of astronomy. We are today September 19th. So this is the start of our week 3. And this is the late start astronomy class. Today, we're going to cover a little bit of basically the laws that govern the object that move in the sky. We're going to focus mainly on one kind of objects, okay? Namely the wandering stars, because ancients, when they looked at the sky, they noticed that some stars, they stay and remain in their constellations and they don't move. So those are the stars of what we call today stars. And then some stars, they change depending on the time, they move, they shift, they don't stay in their place, they don't stay in their constellations. In other words, they don't stay on those recognizable shapes or those asterisms, but they move from place to place to place to place, okay, depending on the year. As a matter of fact, they seem to be moving on the same plane together. That's the ecliptic plane. For where the moon is, for where the sun is, if the sun is on that given time. And what I mean by that is the following. Okay. Today, the sun is during daytime. It's visible in the daytime. Unless there is a solar eclipse, then we will see the stars behind it, and then we will recognize the constellations. So the sun belongs to those constellations. But what happens if there is no solar eclipse? In this case, is 6 months from now, we will see the constellations in the night sky that we couldn't see today because of the fact that the sun is blocking them in daytime, and vice versa. So the rotation of the sun on that plane, and those wandering stars that move in that plane, they're called planets. So the planets are actually all the wandering stars that move from constellation to constellation. They were known at that time, of course, we mentioned them before. Mercury, that seems to be either leading or just behind the sun during the sunrise or the sunset. And Venus, which does a similar fashion, albeit at a greater angle, meaning that it stays longer if the sun sets, or arises a lot earlier than the sun does, as compared to Venus, which seems to be very close to the sun. So that is another wandering star. The third wandering star, of course, is Mars. Mars has a peculiar behavior that was noticed immediately. It's moving in the sky, if you track it down day after day, week after week, month after month, but then at some point it starts to shift, move back in the opposite direction, and then moves forward in the direction it was moving in. So that type of behavior was called a retrograde motion of Mars. So that was a puzzle. We needed to understand that. We want to understand why Mars does that. As a matter of fact, if you look at Venus also, it does that peculiar behavior too. Now we know that all the objects, basically all the wandering stars, they do that. So not only Mars, but also Jupiter also dances around and moves forward. That's another wandering star that was known then. And the last wandering star that was known then was Saturn, albeit Saturn was known from the old times to move extremely slowly versus the background stars, compared to Mars, for example, that moves fairly faster than the other two, than Mars and than Jupiter and Jupiter and Saturn. Okay, so those are the wandering stars. So the wandering stars they were called planets, which really literally means a wandering star, is because they change constellation to constellation. So people wanted to understand what's going on with that. There was some philosophical / religious conditions for what the heavens need to be, okay? And the reasoning is the following. Men on earth have sinned, committed crime, hence things are not perfect on earth. That's why we see valleys, we see mountains, we see hills, we see basically openings left and right, is because the earth is not perfect and has all of this imperfection inherited from the behavior of man. So that is basically the reasoning behind it. Anything in the heavens must be perfect. And if I look at the stars, if I look at the planets, they move they must be moving. First of all, they must be perfect on their own because they belong to the heavens. And also, since they're moving in the heavens, they must be moving in circular paths. The reasoning behind it is the circle is a symmetrical object. It has a center and all the points from it are at the equal distance or equidistant from the center. Hence, the circle is the perfect object in this case. So all of the objects in the heavens must be going through a circle. I mean, if you take a square, it's not as symmetrical because you have one side is more than the other, and so on and so forth. So let me pause the recording quickly in here. So again, the object that move in the sky must be doing the path, they must be going through a circular path. So that was the philosophy, that was the religious conditions for how the heavens need to behave and how the earth needs to behave. It was until Ptolemy in the early, toward the beginning of the Common Era right now, when he put a map basically of all of the known constellations at his time, 48 constellations at that time. And he laid the model where he put the Earth at the center of the solar system, and he put all of the different objects that move around the Earth. Obviously, the moon needs to be very close from the Earth because it moves faster enough. I mean, it does one full cycle in 1 month. Compared to the other object, for example, the sun appears to be a full cycle around 1 year, okay? And then if you take, for example, another object, let's say, for example, the Mercury and Venus, they seem to be following the sun. So they must be probably on the same path of the sun. So I'm describing the Ptolemy basically model. Then he put them in some sort of an onion shell structure, basically where you have the Earth in the center and all of the others moving around the Earth, including the sun. Obviously, this is known as, first of all, it's known as the geocentric model. In other words, the Earth is the center of the solar system. I mean, if you continue in this onion shell structure, you're going to reach at some point the faraway stars that don't seem to be moving, so they're put all the way to the outside, and that's basically how the model ends. As I was saying, there was a problem with the motion of Mars. Mars has a problem, because if it is really moving in a circle around the Earth, so why in the world that sometimes it's moving back and then moving forward? Why does it do a retrograde motion at some points? So here was a problem. This was toward the beginning of the Common Era. About 1400 years later, about 14 centuries later, 15 centuries later, people started to notice that there's a problem with the calendar that Ptolemy put. And the calendar started to shift. Instead of the holidays, for example, the religious holidays that follow the calendar, Easter, for example, instead of falling in its place, it was falling several months later. Christmas, for example, instead of falling in the winter, is falling in spring, and so on and so forth. So the church hired Mr. Copernicus to fix the calendar. That's all his task was. To basically remap all of these objects in the sky, to put all of the different stuff in the sky in such a way that we have them. So the calendar now fits. In other words, the holidays, the religious holidays will be in the right place. So that was his task. Mr. Copernicus immediately recognized that there was a flaw in the whole thing. That the Earth is not actually the center of the solar system. The Earth actually goes around the center, the sun. As a matter of fact, he did a lot of observations and he computed the distance to the stars, to the planets from the sun, and he came up with orders of magnitude, and he came up with some numbers. He put all of his work aside until before he died. Basically, he published it. So this was taking the Earth from being the center of the solar system in the so-called geocentric model, and instead replacing it by the sun, now in what is known as the heliocentric model. So, in order to explain the retrograde motion of Mars for the Ptolemaic model, basically they removed Mars from going around the Earth in a circle, but rather going in a circle where the center of that circle goes in a circle around the Earth. So here's a picture that emerged. So you have Mars going in a circle on its own, and as it's going in a circle, it's moving around the Earth. So now, if you think about it, that can explain it. At some points, it's moving in this direction in the circle, so it's moving normally, but at some other time, it's moving backward, and that is the retrograde motion. So that explains the retrograde motion. There were some discrepancies in the numbers though, but it explains it more or less. And that explains the retrograde motion for a lot of things. But the Copernican model, basically, where he puts the sun instead, if the planets are moving, and he computed the speed with which they move, basically the time it takes for them to go once around the sun, in such a way that the inner ones move slower than the outer ones, then in this case, the retrograde motion is well explained without having to require that the planet goes in another circle, in a big circle, okay? Because as the planet is moving, let's say, for example, this is Mars and this is the Earth is overtaking Mars. So Mars appears to be falling behind, just like when you, for example, when you're driving on the freeway and the person driving next to you is going slower, let's say, for example, doing 50 miles per hour, and you're doing 65 miles per hour speed limit. So you look at and you see the truck moving backward, as if it's moving backward for respect to, of course, you're moving faster than the truck, that's all. Okay, and if it were the opposite direction, for example, if the car is moving faster, it appears to be moving slower than it should be. Okay, at some point. So that's basically it's a relative motion in a sense. So this is how the Copernican model explains this one. So these 3 units, unit 10, 11, and 12, go a little bit through these things, and of course we're going to introduce more in their glory the laws that govern the motion of these objects in the sky. Chapter 10 really deals with the history and how we came from. There are 2 names to retain from unit 10, I should say. Eratosthenes second, and Aristarchus first. Aristarchus was what, about 300 years before the Common Era. And he made some observations based on the lunar eclipse. In doing so, he came up with an estimate of the size of the moon based on how long it takes for the Earth to go once around, for the moon to basically go through the entire cycle of the lunar eclipse. When it's a full lunar eclipse, it takes about 3 hours. Based on that, he came up with the size of the moon to be about 1/3 the size of the Earth. Based first of all on the shadow, and based on the time, he came up with a distance from the Earth to the moon to be roughly about 70 times the size of the Earth. So now he has a size of the moon, which is roughly about 1/3 of the size of the Earth. And he has a distance to the Earth to the moon, roughly about 70 times the distance, 70 times the size of the Earth. Obviously, if he knew the size of the Earth, he could tell you how big the moon is, because all he has to do is take that number and divide it by 3. Obviously, if he knew the size of the Earth, he could also tell you how far the Earth from the moon is. All he has to do is multiply that number by 70. He didn't know that. He didn't know how big the Earth was. Otherwise, he could have answered these 2 questions at once. So all he did was find the ratios of these 2 numbers. Then not only that, he went a step further. During the first quarter of the moon, or the third quarter, it doesn't matter which, he theorized that's because the Earth and the sun and the moon, they make a right angle triangle. And that's correct. It's a valid assumption, okay? Then that distance, basically, if he could measure, and he did measure, the angle that sustains the moon at that time and the sun in that right angle triangle, and he came up with an estimate of 87 degrees. Then he could tell you how far the sun is. Because he knows how far he determined how big the distance from the Earth to the moon was, about 70 times the size of the Earth. And then if he can find that angle, knowing that it's a right angle triangle, using plane geometry, he could tell you how far the distance, what is the hypotenuse of that triangle was. Okay. And he came with a big number, about 20 times the distance from the Earth to the moon. This is wrong. This is well underestimate of what the current number is. But it's important in the sense that the sun is further away from the moon. That's basically his findings. During the lunar eclipse also, solar eclipse, the moon blocks the sun. Since now he has an estimate of how big the moon is, about a third of the time of the Earth. He also have an estimate of how far the sun is. He estimated it to be about 20 times the distance to the moon. And since he estimated the distance to the moon to being about 70 times the size of the Earth, now he could estimate how big the sun is compared to the Earth. That is Mr. Aristarchus, about 300 years before the Common Era. He came up with a number about 7 times bigger than the Earth. Obviously, this is wrong. Now today we know the sun is much, much bigger than this, because part of his problem that 87 degrees, now we know it's almost 90 degrees, 89 point something degrees. So if he used the correct measurement, then he would probably have find better estimates. But his immediate conclusion was the following. Because the sun is bigger than the Earth, it did not make sense to him that the sun revolves around the Earth. It should be the other way around, he argued. The sun is bigger than the Earth. So if it's about 7 times bigger, and we know today is much, much bigger than that, so it doesn't make sense that the bigger rotates around the smaller. It should be the other way around. And here, he ran into a big problem, big time. He couldn't really support his theory. And that big problem is the following. It's called the parallax. You're sitting at home right now. I want you to do the following experiment, okay? Look at the faraway object. Doesn't matter what that object is. Close one eye, it doesn't matter which. And then focus on that object. And then open that eye and close the other eye, okay? What you will see that object does is shifts the location, okay? So again, I'm looking at a faraway object hanging a distance away from me. It's not really that far, it's the end of the room, that's all. Okay. So we would do that in the lab if you guys are sitting in the lab. So I'm gonna close one eye, I'm looking at it with the other eye, then I'm gonna close the other eye and look at it. It shifts. That is what is known as a parallax. They argued the following, and he couldn't answer the question. If it is true that the Earth goes around the sun, they said, shouldn't the stars 6 months from today shift location just because of this? And of course, the answer is yes, they must shift location. There's no question about it. Because if we're here looking at a star over there, and 6 months we're going to move to the opposite side from the sun, the star should shift location in the background side. This is what is known as the parallax, and he couldn't answer that. So his theory was abandoned. So there is a reason. There is a full, good, justifiable reason. And you can do this experiment at home. There is no question about it. For rejecting a theory. And that is because it made an assumption. And that assumption led to an experiment that you could conduct. And that is take a star, it doesn't matter. Arcturus, for example, or Rigel or Ceres, the brightest star in the sky. Look at it today. Note its location versus the background stars. Note its location in the sky. Note it versus the at noon, at midnight, for example, around some terrestrial object and things like that. Note the entire constellation and how it is compared to the background stars. Come 6 months from today, look at the same object. Obviously, you're telling me, for example, I'm looking at something that is near the equator, so 6 months from now, it may not be appearing because it's on the other side. Okay, look, pick Polaris. It's always visible for us in the northern hemisphere, or Arcturus. That's the one I mentioned first. They're visible. Arcturus is visible almost all the entire year. So pick that. Look at it. It's not going to change location. So there is no parallax. It led immediately to an experiment that we could conduct, we could do, and that experiment cannot measure the parallax. Therefore, the Earth, they said, cannot be going around the sun because of that. Okay. Today, the flaw of their experiment, and if you do it outside, is because those stars are very, very, very far away. There is indeed a parallax, but our eyes, they cannot resolve that parallax. That's all. With a finite device that measures extreme small angles, shifts in the sky, We can measure the parallax for the nearby stars, even though they have to be close enough because they are far compared to even our precision equipment. So the faraway stars, forget about it. Okay. So the point being in here is he was right, although the experiments did not lead to the measurable parallax. I think the first time the parallax was measured was in the 19th century. So this is really where we were at that point. Again, Mr. Aristarchus did several things. He came up with the size of the moon relative to the Earth. He came up with the distance to the moon relative to the size of the Earth. He came up with the size of the sun relative to the sign of the Earth. He came up with the distance from the Earth to the sun relative to the sign of the Earth. Obviously, he needed the size of the Earth. That was his problem. He didn't have that. Okay, so that was his major problem. He also made the prediction that immediately he abandoned it, and he abandoned it for good, justifiable reasons at the time, namely that the Earth was moving around the sun, but because his prediction could not really show that the existence of the parallax, it was rejected. Which brings me to the scientific method. If you're going to make an assumption about something, just to explain something that was seen before, that is not good enough. You have to make predictions. And those predictions, they should be able to be tested. And if you test them and your prediction is correct, so far, your model gets a check mark. And you keep on check marking until it becomes a theory. If it fails once, you have to abandon that assumption. And that is exactly what happened in this case. So again, his problem was he was missing the size of the Earth big time. He didn't have that. So he needed that. But at that time, he was basically, that's the extent with which he ended. Then Mr. Eratosthenes in Egypt heard of a city in southern Egypt, which is now called Aswan. In the old days, it was Sayan, or depending on how you say it. It's modern day Aswan anyway, which is almost to the border with the modern day Sudan. At that time, there was no border. So, okay. And where during the time of the year, namely the summer solstice around June 21st, the object do not have shadow. So if you have a stick on the ground, that stick does not have a shadow, zero shadow, basically. If you look at a well, for example, that well will, you will see the sun inside the bottom of the well in that place. In the same time, if you are in Alexandria, which is in northern Egypt with the Mediterranean Ocean, Mediterranean Sea, you will see that objects have a definite angle, definite measurements, okay? And that angle is actually a definite shadow, and that shadow will make a 7-degree angle on that same time of the day. So he made an assumption in here that because this can only be explained if the Earth has some sort of a spherical shape, so it was a sphere. And he, using geometry again, he was able to determine the size of the Earth that Mr. Aristarchus was missing. So let me share with you, first of all, the notes. We find them first. Show more windows. Okay, here it is. Again, these are the objectives. So hopefully you guys are doing the reading and going through all of these notes. They're just supposed to help you. It's still the reading because you're going to be tested on these things, okay? Are you guys looking at the PowerPoint in here?
Yes.
Okay, very good, thank you. Anyway, so again, first of all, one of the arguments for the shape of the Earth, this is an old, outdated argument, that the Earth is actually spherical in shape, okay? One of the reasons for it is that if you look, for example, at objects in the ocean, near the ocean, for example, near the sea and the port, for example, what you see in here is the boat starts to disappear from the bottom up, meaning it starts to fall below the horizon from the bottom, okay? If the Earth were flat, the ship should disappear, should shrink in size, but retain its shapes. In other words, you will see the bottom and the top together until it goes into infinity, until you cannot see it no more, okay? But the objects, because they fall below the horizon, as they fall from the bottom up, okay? And if you look at the city in here, I think this is Lake Michigan, near Chicago, what you see in here is the bottom half of the city is missing, okay? It fell below the horizon. Buildings, you will see the top of the building, not the bottom of them. Because again, there is a curvature, and those are the ones that are falling behind the curve. So again, the argument for why the Earth was spherical is an outdated argument from the time of Aristotle, okay? So this stuff that you see on YouTube are clickbait, basically. They want you just to click on them to watch their videos so that they get more and more followers and then make more money through advertisement. No more, that's it. Because they know themselves these things too. And they start to arguing on all kinds of some sort of conspiracies and nonsense like that, but it's not based on science. These things are known from a long time. The other thing also argument that was made is based on the lunar eclipse. The lunar eclipse was thought of, justifiably so, that it's the shadow of the Earth projected on the moon. And that shadow, when it's a partial lunar eclipse, is always has an arc on it, okay? Starts from an arc and it's continuing arcing until it completely ends in another arc. So here is the situation. If the Earth was flat, the sun has to be always from this position this way. But if the Earth is tilted a little, then we'll see just that part of it. As a matter of fact, if the sun is coming straight out at the thin size, we should only see a line. That should be the projection of the Earth on that side. So we don't see that. So his argument then, hey, the Earth must be a spherical object because whichever way it rotates and which way the sun comes, it always produces those arcs in there for the during the lunar eclipse. The other observation also is stars that are seen at certain points in certain locations. As you travel south or north, you're going to miss stars, or you're going to see stars that you didn't see before. Stars you used to see, they disappear, and stars that you didn't see appear again. Why? Because those, they fall below your line of sight as it passes through the horizon, and new ones that you didn't see before appear above the horizon. So that is the reason why the Earth cannot be not spherical. It has to be spherical. So those are some of the reasons that were put forward several decades before the current era. So this is some ancient stuff, well before YouTube. Now YouTube is there and it's taking advantage of some basically conspiracies and making all kinds of nonsense stuff. Again, the distance and size of the sun, this is basically what Mr. Aristarchus basically has argued for. And it's based on this measurement of this angle, okay? If you look at the sun, when it's setting, of course, this is when the first quarter is, this angle must be in the right angle triangle. That's his argument. This is the 90-degree angle. So now all he has to do is measure this angle. And if he knows the distance to the moon, which he already did make an argument for it, so the distance from the sun to the Earth is about 20 times the distance from the Earth to the moon. That's all. If you know this angle alpha in here, or A, is it alpha? Alpha. Yeah, and this angle beta is going to be assumed to be 90 degrees. His measurement was 87 degrees. That's all, okay? And that is not correct, okay? So that is far more than that. If he did the correct angle and he uses the arctangent, he would have, or the arc, in this case sine, he would have found the correct value. But that's the best he could have found. But indeed, this distance is much, much bigger than the Earth-Sun distance, and that is basically his bottom line. This distance now we know is 384,000 kilometers, whereas this distance is about 150 million kilometers. So it's far more than 20 times bigger. The other estimate also was for how big the sun is compared to how the Earth is, okay? His number came up to be about 7 times bigger. But today we know the radius of the Earth is about what, 6,400 kilometers. The radius of the sun is 700,000 kilometers, 698,000 kilometers. So this is about 100 times, actually slightly more than 100 times bigger, okay? So this estimate of 7 times bigger is not correct. But his point again is that, hey, listen, the sun is bigger than the Earth, so it doesn't make sense that the sun revolves around the Earth. That's basically his point in here. And it could not really be well sustained. And the other estimate that he came up with, based on the lunar eclipse and how first of all, how many times the sun basically will cover the moon. I mean, how many times the Earth will cover the moon as it goes through it? It's about 3 times. So he estimated the sun of the moon, the size of the moon, to be about a third the size of the Earth, and that is slightly off because again it's 0.27. The radius of the Earth is about 6,380 or 70 kilometers. The radius of the moon is about 1,700 and something, 1,748 kilometers. So it's slightly less than a third. That's the point in here. So this number is not off, as a matter of fact, okay? And also the distance to the moon based on the how long it takes for the moon to go around the during a lunar eclipse, and how long the moon takes to go around the Earth. It takes 27.3 days, and it takes 3 hours. You take the number of days, which is 27.3, and you multiply it by each day has 24 hours. So you come up with about 660. You divide that by 3, and you do the math. You'll find about 220. And there is another math in here that you're going to do. That is actually the diameter, the size, but then you have to divide by pi in this case to find how big it is with respect to 220 divided by pi is about 70, okay? So it's about 70 times the size of the Earth. That's basically what it is. 220 divided by 3 point something is about 70. This is not correct. We know today is only about 60 times bigger, okay? Again, but he's got you good numbers. So yes, the size of the sun and the distance to the sun, they were off, and they were off due to this measurement of this angle alpha. But the size of the moon and the distance to the moon, they were actually close from the correct answer, okay? So they were not far. So that's basically what his thing is. Now, the problem, as I was describing earlier, is the parallax. If you are true, if what you're saying is correct, then we should shift the entire sky. The celestial sphere should shift back and forth as we move around the sun. And that we don't see. And today, so his argument that the Earth goes around the sun did not hold water because we couldn't see the parallax, the shifting, that the experiment that I was describing, okay? Today we know we do see them, but it has to have very high precise equipment to see them. Then came Mr. Eratosthenes, okay, as I was describing in the beginning. And he noted in Alexandria, the shadows make 7 degrees, okay? Remember, before him, Mr. Aristarchus already argued that the sun is about 20 times the distance from the moon, okay? And the moon is about 70 times bigger than, further than what the size of the Earth is. So you're looking at a huge distance to the sun. So the sun must be very, very far, very, very far away from the Earth. That's basically the argument that Mr. Aristarchus made. Because of that, then the rays that are coming from the sun must be all parallel. Why? Because they're coming from infinity as far as we're concerned. They come from infinity. And people at that time, they knew geometry. They were very good with geometry. So rays coming from infinity, they all come at parallel lines. In the city of Siam, they don't produce any shadow, and the well will be basically the sun. You can see its reflection in the center, in the center of the well. So the rays, they come straight out, and the rays are coming straight out everywhere on Earth at that day. On Alexandria, they're coming out. So the ray that is hitting the city of Alexandria is passing parallel to the ray that is hitting that city. And now 2 parallel lines, because the Earth has a spherical shape, again, the arguments before from Aristotle. 2 parallel lines cut by the same line, these 2 angles must be the same. So the angle sustained by the distance from Siam to Alexandria is 7 degrees. And because they were very good at geometry, then he could find the circumference of the circle. All he has to do is take 360 divided by 7 times this distance. That's all. At that time, the unit of measurement was stadia. How many stadiums are, the stadium length, which is about 100 meters, how many stadia are between the city of Siam and the city of Alexandria? I had a bunch of people and they gave him measurements. So then he multiplied that by the ratio of 360 divided by 7, and he came up with a number very close from what we know today, 40,000 kilometers if you can take the stadia about 100 meters. So his number was very, very, very good, okay? Just because of this geometry thing. So now we have the size of the Earth. So we can answer how big the moon is. Divide that by 3, because we can find the radius, we can find the diameter, we can find all of the things. The radius and the diameter are related to the to each other, to the circumference, which is this whole distance going through a whole circle, and this is the radius r, or the whole thing is just the diameter, whichever way you like. It's pi times the diameter. Since now you know the circumference by just dividing 360 by 7 times the distance to Alexandria from Cyan, you're going to find about 40,000. So you have the circumference. If you have the circumference, you can find the diameter. Pi is a number. Pi is 3.17, 3.14. If you find the diameter, all you have to do is you divide that by 2, and you have the radius. So you know exactly how big the Earth is. Since you know how big the Earth is, now you can go back and work your way through and find how the distance, which is about 70 times, now we know it's not correct, slightly less, multiplied by this diameter. And then how big the moon is. In other words, what is the diameter of the moon? All you have to do is take this diameter and divide it by 3. How big the sun is? All you have to do is take the diameter of the Earth and multiply it by 7. That is not correct today. It's far more than that. It's multiplied by 100 to be more specific, okay? Take the, you want to know how the distance to the moon, to the Earth, to the sun? Just take the distance that you computed earlier for the sun, moon, and then multiply it by a factor of 20. So you have all kinds of things now. You could theoretically do all that you want. The reason why I'm setting up this thing in here, because can you hear me?
Yes.
Okay, sorry about that. Please don't leave if something like this happen, okay? Okay, very good. Anyway, so I don't know where I got stopped. But basically, the argument I was trying to make in here is that knowing the size of the Earth now can let us do whatever we want to. And the other point in here I was trying to make is that by the time of Mr. Newton, he has an estimate. He has the distance, the Earth to the moon, and he needed that. It's very important that he needed that. He also needed the force of gravity, which was, I mean, the acceleration due to gravity, which was known at that time by Mr. Galileo. But he needed this number, and its number is coming from here. The distance to the Earth to the moon, and also the distance to the sun and all of these things. So he needed those numbers. Of course, there were better measurements that he needed for the distance to the sun. But again, they were actually performed better later on and so on and so forth. But this number is needed from the distance from the Earth to the sun. And one of the reasons that was improved actually for the sun is because of that measurement of this angle. This was refined further, and that angle was found better. So the distance to the sun was actually refined better than what Mr. Aristarchus found. So again, we're looking at ancient times. People have no basically lasers, no far more advanced technology that we have today, but they were able to determine all kinds of things with very high precision. I mean, relatively speaking, with extreme good numbers, so that they can still work, okay? This is the argument basically that I was talking about in here onto how to find actually the size of the sun if you know the size of the moon. This arc the size is part of a circle. So this is an arc, actually, length. And this is also another arc length, which is the size of the sun, okay? They both sustain the same angle alpha. But one of them, this is the radius, this is the distance with which you're looking at, and this is the other distance that you're looking at. For those sitting in Astronomy 125 in the lab version, this we use it actually in the first lab with the cross-staff to find how far the objects are, and I'm sorry, how big the objects are if we know how far they are, okay? If we know some sizes, okay? So all you have to do is take just an object, like a quarter, for example, and block the sun from it, measure this distance, know the size of the object, and then if you know that distance, you can use that using the simple geometry. In other words, the angle usually is measured in radians, but you can still work with degrees if you like. All you have to do is divide by 360 instead. And this arc ratio and this ratio are the same ratio as this radius and this distance. That is in a nutshell what we're using, okay? So the formula in here is the size of the object, which is its diameter typically, okay? And there is a problem that we're going to have in here trying to find the size of Jupiter using the same analysis based on how far Jupiter is to us. So this distance is needed, okay? This is D. And 2 times D is actually the circumference. So this distance is D, not the diameter. This is the radius of the circle. So the distance is D. So 2 pi times D, 2 times D is the diameter, is the circumference. If I take that and do the ratio of the actual size, this size of the object over the entire circumference, it's the same ratio as this angle alpha measured in degrees over 360 degrees. Because typically we use radians. If you use radians, then you're going to have a different thing in here. It's going to be just the angle times that distance, okay? So here is the formula that is actually, we use this in the first lab for those sitting in the lab. If not, in your problems, this you're going to use it to do the size, for example, of Jupiter and the problems and so on and so forth, okay? Okay, it seems like we still have good time, so we can jump into the next unit and actually talk about it. And I know in the introduction I talked a little bit about it too. So let me share more windows. And where is unit 11? Here is unit 11. Okay, so in here, we're looking at those wandering stars, basically the planets, the geocentric versus the heliocentric model. And the position of the stars, this is geometry that Mr. Copernicus has introduced, namely, look, now we're putting the sun in the center. Planets like, for example, Mercury and Venus are inside the path of the Earth. Mars and Jupiter and Saturn, they're outside of the path of the Earth. At some point, these are going in a circle. These are going in a circle. And let me emphasize on the word circle, because he thought the circle also still hold true. And this is the Earth also going on a circle, and so on and so forth. At some point, the Earth will be here, Venus will be here, or Venus will be here, or Venus, it could be here. It could be in any of these points in its path. Same thing with Mercury. Mercury could be here, if you like, or here, or anywhere in its path, okay? Same thing with Mars. Mars could be here, actually, nothing there. And same thing with Jupiter. Jupiter could be here, and Saturn could be here. As long as they're on their own path, there's no problem with it. They could be anywhere on the path as long as we take any point of reference. Now, he has some determinations in here, okay? When they're lined up in here, he uses the word conjunction. And you have to really take inferior or superior conjunction, depending on where they are, versus opposition. And this geometry played a major role in here. There is a line of sight in here. If you take, for example, Venus is moving in this arc. and you can see it, but then is going to move back. For me, looking at this angle sustaining the path of Venus, I can see Venus going only left and right. So at some points it's moving this way, and later on it's going to be moving backward in here. So this geometry helped him a lot in finding, this is Mr. Copernicus, of course, finding the actual distances and the times it takes from here to there, from here to here, from here to here, for example, for the case. This angle is a lot less, for example. So if I look at Mercury versus, for example, Venus, and I'm sitting in here on Earth, this angle is much bigger for Venus than it is for Mercury, because it's smaller, the path is smaller. Obviously, the geometry is different for these outer planets, okay? But they also do have the same behavior. At some point, I can see Mars, and then at some point, Mars is going to be here, and this is, then after that, it's going to be sustained in that arc again and come back off of it in the opposite direction. So there is that analogy, if you wish, as long as it's in this side, in the opposition, rather than in conjunction. So planetary geometry, or actually is an interesting one. It helped Mr. Copernicus come up with the numbers. So again, the planets, they move around the, now we're talking in the time of Mr. Copernicus, they move around the sun, and the Earth also moves around the sun, okay? This is the time of Mr. Copernicus, the Earth is tilted, and that is basically what it is. Before that, there is the geocentric model. In the geocentric model, the Earth is here, and everybody now is going in circles around the Earth, okay? So that is basically, and this is due to the yearly, at least for the case of the sun, it's the yearly motion. For the case of the moon, it's the lunar month, and so on and so forth, okay? As I was saying, there is this peculiar motion that some of the planets exhibit. So if I take Mars, for example, it's moving from February 2016, it's moving forward. At some point against this constellation, and I see Antares in here, the star, it's moving backward and against the constellation stars. And then it's moving forward. So come September of that same year, it's moving in the same direction. Actually, it started in retrograde motion well after February, sometime in here, and then it moved back, and then for several weeks, and now it's moving in the same direction. Same thing with Saturn, by the way. Okay. So all of these objects have this retrograde motion. Again, we needed to explain that. Any theory you come up with need to explain this thing. So again, you have Mercury, you have the moon, of course, very close from the Earth. And then you have Mercury, you have Venus, you have, did they put Mercury because it moves faster? Yeah, it moves faster because, and then, so this is the model basically that you have, and versus the background stars that don't seem to be moving. They don't bother. They're sitting in their own unique constellations or asterisks. Whereas these things, they move back and forth around those things. So they were called planets, which literally means a wandering star, okay? So now we needed to explain that retrograde motion. And I was saying this is basically the epicycle pattern that was defined for the case that exhibits retrograde. So it's moving in the same direction for most of the year. Then at some point, it's going to move back in a circle whose center goes in a circle around the Earth. So this is basically what the Ptolemy model basically explained as far as the motion of the planets around the sun, around the Earth, I'm sorry, with the Earth being in the center, and that's how that justifies the retrograde, okay? There is a problem though. This motion is real, backward motion is real, if this model is true, okay? And if it's that, what causes to do that? That's the biggest question that people wanted to understand. This is a real motion in the opposite direction. So you have somebody going one way and then changing and then going the other way. So what causes him to do that? Why can't he just move in the same direction? Whatever causes him to move in that direction, keep on moving in that direction. So that was a major flaw in the geocentric model that nobody could answer. Because that motion really required the planet, like Mars, to go back in its motion. So what is causing it? So it must be tethered somewhere in here, and there is a force that pulls it toward that center. That's basically what needs to be, as opposed to a force that keeps it from flying away from the Earth. So if you take, for example, a string, and you hold the rock in it and you tie it to one end and you start spinning. So there is that string that holds that rock from flying away from your hand. Case in point, if you cut it, it's going to fly away. So it seems that whatever causes the planet to be retained to the Earth, that's fine. We can probably later on talk about that and come up with an explanation for it. But there is a mystery in here, and that mystery has to do with this central point where the planet also seems to be tethered there too. So what holds it there? Why? What is there? So there were some questions about that the geocentric model couldn't explain. Whereas in the heliocentric model, where the sun is actually in the middle, all I have to do is explain what holds the Earth to the sun, what holds the Earth to Mars, and I'm in business. And that's exactly what Mr. Newton did. He came up with the law of gravity, and the gravitation in this case is universal, and it holds everything to everything else. Any mass attracts any other mass, with the exception that the sun is much, much bigger than the Earth. So it's in the center and it's attracting everything, and everything moves around it. So that is it. But then that also explains the retrograde motion, because if the Earth is moving around the sun faster than Mars does, and it does because of the way that these things move, then the Earth, as it's overtaking Mars in its rotation, it appears that Mars is moving backward versus the background stars and the constellations and the night sky. So it looks like Mars is overtaking. At some point, it's going to start moving forward. So there is no need for another circle, another circle, another circle, and there is no need for a magical force that must exist to explain the real motion. This is not a real retrograde, though. This is a virtual retrograde, as opposed to a real retrograde in the first case. So that is a big distinction here that needs to be made. Okay. Again, as I was arguing earlier, you have a conjunction for the did I give it backward? Yes, I gave it backward. Sorry about that. Okay. So the opposition is when it's opposite to the sun. Okay. And the conjunction was in the same direction as the sun. You have an inferior that is between us and the sun, and the superior that is in the opposite direction. And that is basically the different position. So he came up with all kinds of geometry and explains basically the position of the planets. In doing so, he was able to come up with some distances. Okay, please read about the quadrature in this case, where the position is opposite to the Earth, making a 90-degree angle in this triangle. And this is his measurements, actually. Of course, the sun just went down, and both of them are following it. The greatest elongation, which is this angle, actually. Let me go back. It doesn't matter which one it is. Okay. So for the case of an inferior conjunction, so this is the Earth. This is your greatest elongation. Okay. This is the greatest elongation, that angle. Obviously, for an inner planet like Mercury, the elongation will be smaller. And that's exactly what he noted too in here in his model. 28 degrees for the maximum, basically, that you're going to find for Mercury as it ventures away from the sun. And the maximum you're going to find for Venus as it ventures away from the sun is 47 degrees. Using all of this geometry and the time it takes for them to revolve and how long it takes and all of that, he came up with these numbers for how far these objects are from the sun. Mercury is, he estimated it to be about 0.38. We know today is 0.39 on average, so he was not too far. Venus, he had it right on the money. Exactly. About 0.72, the distance. The Earth, of course, is the standard. That's the candlestick. That's the one that you measure things with respect to. Mars also was very good. Now he starts to deviate when you go into, for example, Jupiter. Instead of a distance of 5.2, which we know today is the distance from the sun to Jupiter, he came up with an estimate of 5.22, okay, which is slightly off, not that much really. And then it was way off actually for Saturn. Those are the objects that were known then at this time for the how far they are, at least the planets that were known then, okay? He didn't know about Uranus and Neptune. Okay, so those were discovered later. So this is the Copernican model. So we went from the geocentric model to the heliocentric model. Obviously, that was a major revolution. That caused some problems for some people, including Mr. Galileo, who believed in his work, and he made a lot of arguments for that. And he took a toy, which we're going to talk about next time around when we meet. And that toy at that time was a telescope, actually. And he modified it a little, and he looked at the objects in the sky. And the first thing that he found is that the heavens are not so perfect after all. There are hills and valleys in the moon. So the moon also has some problems. It doesn't look, it's not as smooth as it may look like that you can think of. And then furthermore, he found that there are objects, because the church was against this idea of the heliocentric model big time. There are objects that move around something else other than the Earth, namely the 4 moons of Jupiter. They don't revolve around the Earth, they revolve around Jupiter. And he was able to document their period and how long it takes for them to go around Jupiter. Okay, the next unit, I really don't want to start it now, so we're going to finish it next time around when we meet. And we're going to do some discussions of problems from this units because they're interesting. Is going to be unit 12. And don't forget, you have quite a few things to do this week too. Let me go back into my into the class models. So we're in week 3. So let me share the screen with you guys. And that's what we're going to do next time so that we can move along too. So share. So we have this 3 units. Unit 12, we're going to defer to Wednesday. We have the objectives in here, typical content stuff, but there is 2 types of assignments. So we have a quiz, which now I hope that you guys are accustomed to. The recording is going to be here, but we have 2 homework assignments. You are strongly encouraged to do them. But before that, what we're going to do on Wednesday is take some of these problems and we discuss them in detail, okay? We're going to actually do them. The whole point that I'm trying to have you do, guys, is that I believe in the power of the homework. It helps you understand a lot of these things and have these things sink better. And it's only when you do things. You could read as much as you want. You could engage in discussions. You could also watch videos. You can attend class. You can do all kinds of things. But unless you really honestly take a pen and start writing and plugging the numbers and see how big they are. The type of calculations in here are not really honestly hard. All you have to do is take a number divided by number and see the ratio to things, how they are. Either they are too small or too big or the same. So you compare this to that and they are the same, or I compare this to that and this one is much, much bigger than the other one, or vice versa, the other one is much, much smaller. So those are the type of calculators. At some point, we're going to get a little bit more involved by doing and adding and subtracting, but at the end, we're going to get into some better estimates. So the whole point in here of this homework assignments, which are straight from the book, okay, and both of them are due next week, October 1st, which is not this weekend, the next weekend. They're intended for you to reinforce all of these concepts and help you understand better the material. Sounds good? Here is the promise, though. I'm going to do some of them with you guys live. Thank you, Gladys. And then I'm going to also ask you guys to do them, also again, redo them if you wish, to submit them, and do the remainder. And now, if you have an issue, if you don't understand one of them, or if you don't know how to start it, please let me know. We can do a one-to-one session, either on Zoom or in person on campus. I know that my office is still not ready, but we have the STEM Center. We can meet there too. We can actually go through that same problem. And if it's something unique to you, that's fine. There's no problem on it. But if it's something that benefits the entire classroom, I will ask with your permission, if it's a Zoom session, to record it, or at least to record that portion, and you will be very well of it. So you will know exactly what is recorded. And then basically take all of the particular information to yourself, and then share it with everybody else to benefit the entire classroom. So this is the intent. This is the plan. So I hope you get to see you guys on tomorrow we have lab for those sitting in astronomy 125. For those who are not sitting in astronomy 125, then never mind. Tomorrow we have lab, and then we also have a session on Wednesday. I'm going to stop the recording, and I will see you guys Wednesday. Sounds good?
Yes, thank you.
Okay, thank you guys. Bye.